Okay, go ahead. My name is Ian Luo. Victor Ding and Jimmy Kwon. And we also have Alexander Michik somewhere in the audience in Ottawa. Alex is the key contributor of GC technology for this project. So we're here to talk about software-based concurrent scavenge. Concurrent scavenge is also known as positive GC. So you've probably heard of the hardware-based implementation. And what we're here to talk about is a pure software-based concurrent scavenge that brings near concurrency to a mainstream IBM GC policy. Okay.
Ian, I'm sorry, before you start, could you maybe get a bit closer to mic?
Yeah.
Oh. Thanks.
What this says is if we made a mistake or we said a bunch of things that are false, we're not going to be held accountable. Agenda, we're going to approach this from both a GC perspective and a JIT perspective with some little bit more emphasis from the GC side. So we're going to provide a background on GenCon, and we're going to talk about scavenge, all the key pieces of technology that implement scavenge. We're also going to talk about concurrent scavenge, what makes the scavenge collection concurrent. And then Victor is going to talk about JIT's role in implementing the CS policy. He's going to talk about the common code support for concurrent scavenge. And then Jimmy will talk about the cogen support for CS and its implementation on Power and x86. And then I'll come up and talk about our performance tuning efforts and any future work that's in the pipeline. So first, just a little bit about Java heap. So the Java heap is where the Java objects are allocated from. On one hand, you have -x and s, which is the maximum amount of heap. It is a contiguous range of reserved address space that's initialized as product. On the other hand, you have -s and s, the initial or minimal heap. That's basically the committed portion of the memory out of the -x and x. And heap under GenCon is divided into multiple segments. So you have tenure space where the old objects live, and then you have nursery space where the newly allocated objects are. And further, the nursery space is sub-allocated into allocate space and survivor space. More on these later. So an overview of GenCon. So GenCon is our default GC policy. It stands for generational and concurrent. And the generational here applies to nursery collection that only collects the live objects in the nursery space. We don't touch the tenure, the old space. And generational collector is also known as a scavenge collector. So the concurrent in GenCon applies to software world global whole heap collection. And the concurrent here means that only part of the global collect operation is made to be concurrently running with the application thread. And under a well-tuned GenCon policy, global collections are relatively rare because they are very expensive. You had to collect the entire heap. So almost predominantly under a GenCon policy, well-tuned, most of the positives are contributed by the nursery collection. And our talk, concurrent scavenge, basically means that the scavenge collector is now made to be running concurrently with the application thread. So that's GenCon. Now focus on scavenge. So the guiding principle of a scavenge collector is objects die young. So most objects, they only live for a very short period of time, so we can discuss them quickly. So the heap under scavenge is divided into the nursery new space and the tenure old space. And the nursery is collected with a copy collector. So you have a bunch of objects in the nursery space. It gets full. So the next thing you will do is the GC will basically find out of these objects which of them are live, and then just copy them over to the appropriate destination space. So continuing on scavenge, most objects are allocated in nursery space. And there are special objects like classes, integer strings, large arrays, large objects are pre-allocated into the tenure space because the assumption is these objects tend to be long-lived. So nursery is divided into two halves, the allocate space and the survivor space. So when the allocate space runs out, we find which objects are live, and then we copy them over to the survivor space. And then the next thing the GC will do is it will switch the name of the allocate space and the survivor space, such that the old survivor becomes the new allocate, and the old allocate becomes the new survivor space, such that when the GC is finished, applications resume, they will allocate newly allocated objects into the new allocate space. So every time an object from allocate space is copied over to the survivor space, it's called a flip. So every time an object is flipped, its age is increased by 1. The age is encoded in the object header by a few number of bits, and if the age of an object exceeds a certain threshold, the next time it's flipped, it's not going to be copied into the survivor space, but rather it will be copied into the tenure space. The reasoning is if the object has survived a few garbage collections, okay, it's probably not going to die soon, so we're going to just move it into the tenure space such that, in the next scavenge, we're not going to be bothered by it to save some time. And the threshold of this aging is determined dynamically by the GC with some runtime heuristic. And these age bits can range from between 0 and 14. So when the scavenge copies an object, what exactly happens when a scavenge copies an object? So here you have an object that the GC reaches through tracing the object reference graph. You have header and you have data. So every GC thread that does the copying will have a chunk of memory that's thread local, that's private, that's allocated from either the survivor space or the tenure space. So that memory is private to the thread. So the next thing we'll do is, let me just go ahead and copy the object over. So after that, the next thing to do is, it will replace the header of the old object with a pointer to the newly copied object. It's called a forwarding pointer. And this is done atomically using a concurrent swap instruction. And the forwarded pointer is low tag, such that you can differentiate between a forwarding pointer and a regular reference field. So the installation of the forwarding pointer is atomic. So in the case multiple threads come across on the same object, they all try to copy, and it would just go ahead and with the atomic concurrent swap. One thread will succeed, it will update its reference, it will install the forwarding pointer, update its reference. All the other threads will say, okay, somebody beat me to it, I'm just gonna forget about my copy and then use the forwarding pointer that's already there to update my location. So that's really the advantage of this algorithm is really the atomicity ensures that the copy and installation of the forwarding pointer happens in one pass, and it doesn't require any extra memory. So that is scavenge copy. So in the concurrent scavenge, how does the copy work? So regular scavenge, the thread that does the copy is the dedicated GC thread. And the concurrent scavenge, in addition addition to GC threads copying objects, you also have application threads running concurrently with the GC threads that helps the GC out by copying some of its objects that it comes across. So more specifically, when the application thread executes, every field load that it encounters, it will examine the reference object, see if it's in the survivor space that I need to collect, and if so, it will copy the object over using the exact algorithm I described in the previous slide. And together, the application thread and the background GC thread, they will basically finish the task of tracing the entire object reference tree to basically complete a GC cycle. So that is concurrent scavenge copying. So I talked about how we do the copy. So what do we copy is the next question. So how does scavenge determine what objects are live? We start from a set of objects called roots. A root object is where we trace the object tree from. They are typically contain graph stacks, class static. So basically you go from the root set, and then from there you can reach the entire set of live objects via tracing the entire object reference graph. So in order to find all the objects that are live in the nursery space, we need to go from the root and trace all the object tree. And we actually need to trace every object in the tenure space because the nursery collector, the scavenge, is a nursery collection. It's a nursery collector. So it doesn't really touch any object in the O space. So if we trace all the object graphs, a lot of it is going to be in the tenure space. And we're not going to collect them. So that seems a little bit wasteful. So it turns out we don't need to trace all the objects in the O space. We only need to trace a subset of them, namely the objects in the O space that has reference that points to allocate space. Those are the objects that we're interested in. So in this case, we have two objects in O space that points to the allocate space. So the GC will have a data structure like a collection that basically keeps track of all the references to the O object that has pointers pointing to the new object. So in this case, and that collection is called remember set. So in this case, the remember set will keep track of those two object references in the O space because they are very interesting to the scavenge. So in this case, the remember set becomes a refinement of our live object set. So basically, we only need to trace the root and the remember set in order to reach all the live objects in the nursery space. So from an application standpoint, you've probably heard of a term called write barrier. So the remember set is enforced by the concept of write barrier. So every time the application thread executes it writes an object into a reference field of another object, a piece of code called write barrier has to be executed. So what the write barrier does is it will check both the range of the destination object and the source object of the put field operation. So if the destination object is in O space and the source object is in allocate space, creating a red line. So in that case, if the object has not already been remembered, we are going to insert reference to the object into the remember set and set a bit in the object header to 1, so that the bit is called a remember bit, such that when another thread comes across that object, it's not going to be remembered twice. So that is scavenge remember set. So now I've sort of covered the key concepts involved in the scavenge collector. I think we can talk about timing for the regular scavenge. The regular scavenge is a stop the world collector. So that means every application runs every application thread runs freely until we run out of space in the allocated space. Nursery gets full. So at that point, every application thread must be stopped, and the scavenge will take over. It will trace the root set and the remember set, reach all the live objects, copy them over, and then that concludes the GC cycle. And at that point, the GC will stop, and the application thread will be able to resume. And then the whole process starts over again. So the GC pause under a regular scavenge is called a scavenge collection cycle. So how does concurrent scavenge differ in terms of timing? So under concurrent scavenge, application threads run until run out of space in the nursery, and then we'll also incur a very small initial pause in the GC. So that is also a stop the world GC pause. But the difference is this pause is very, very short, in which the GC only scans the root set, the thread stack, and a few other very fine-grained small set of root objects. And the GC will copy them over, collect them, and the GC will stop right away. So such that the initial pause is very short. So the GC finishes the initial pause, application threads can resume, and then they resume right away. And the difference is now the application threads need to help the GC out by doing some GC work. So what does the application thread do? So every time they come across loading of a reference field, they need to look at the field to see if it needs to be collected. If so, copy the object, and then continue on. So the application thread executes along, and all the reference field it encounters during this execution path will be copied over. So that's the application thread's job during a concurrent scavenge collection. So on the other hand, we have a number of background GC threads that basically does the old-fashioned tracing of the object graph. So it's basically they pick up any flag for the application thread. So together, the application thread and background thread will completely trace the entire object reference graph. And when that's done, another pause will occur, also a stop the world pause, in which the GC will basically do some finishing up, bookkeeping, and then when that's done, the application thread can resume. But this time, when they come across a reference field, they don't need to count the GC out because there's no collection. Collection is over. And then the whole process starts again. So from the end of the initial pause till the beginning of the final pause is what we call a concurrent scavenge collection cycle. And because the application thread now runs concurrently with the background GC thread, obviously now the concurrent scavenge collection cycle would be longer than the scavenge collection cycle, which is basically a stop the world collect. And from the end of the initial pause to the beginning of the final pause is what we call a concurrent scavenge in progress. During this period, the scavenge machine will set up certain flags and initialize certain variables to indicate to the application thread when you come across a reference field load, you need to do something special to help the GC out. So that is the concurrent scavenge overall timing. So now I'm going to invite Victor to talk about the JIT work.
Thank you, Ian, about give a good talk about the GC side. Now let's look at the JIT side. So as you can see, the app thread now involved in GC work as well. So most of the application thread are JIT code, hence the JIT needs to generate logic to coordinate with GC. So now let's see how let's see what JIT needs to do. So under concurrent scavenge, loading a reference isn't a simple instructions anymore. So once we read a field, we must check and see if GC's involvement, if GC's involvement is required. So if we need GCs, then we must notify GC to perform things like object copy or like other related bookkeeping. So so luckily this step is transparent to JIT. GC provides a helper that JIT can simply call so whenever necessary. And once GC finishes work, then it will give control back to JIT, and program continues. So the key is to determine whether GC's involvement is required. It can be done by checking if the recently loaded reference points to a memory region that's specified by GC. So in short, we need a range check here. So currently, luckily, we first developed this thing on the concurrent scavenging thing with a hardware approach on IBM Z machines that has a guarded storage facility. So that hardware, so Z14 hardware provides instruction set that can guard up to 64 contiguous segments of contiguous memory, and has two guarded load instructions, which is load guarded and load logical and shift guarded. And the first one is used for the non-compressed case, and the second one is used for the compressed ref case. And the instructions behave just like an ordinary load, but they would trap when the recent loaded field points to the guarded region. So and then the signal handler will notify GC for its work. So as you can, so with the guarded storage facility, here is how concurrent scavenge works. And once the instruction reaches the guarded load guarded instruction, the instruction will perform the range check after loading the reference, and it traps if the loaded value points to the region. And then the signal handler will notify GC to perform its required work. But here, I believe the signal the signal handler is a specialized signal handler crafted for the purpose of a concurrent scavenge here. It is much lighter than the other signal handler that handles other signals like NPE or others. So once GC finishes, the application resumes back to the load guarded instruction, and then this time it shouldn't trap anymore, and so application continues. So what if there is no such thing as, what if there's no guarded storage facility? For example, on x86, on Power, on ARM, or many other architectures do not have such an instruction set. Then, to achieve the same function, we implement a read barrier in software. So what is a read barrier? The read barrier is a generic concept for loads with side effects. So we introduced a group of low-IO opcodes to represent read barriers. The opcode are also used by FieldWatch as part of the full-speed debug framework. E had a talk on the last compiler mortality talk. But anyway, so there are as many as read barriers as load opcodes, and each read barrier corresponds to one load opcode. But so for the purpose of concurrent scavenge support, only two opcodes are needed. So we use the I read bar I for compressed ref and A read bar I for the default mode, just corresponding to the hardware instructions. The I read bar I would be the load guarded shift storage and the load. Yeah, there are the other the instruction, and the A rebar I corresponds to the load guarded instruction. So as you can see, so now we can see the rebarrier of concurrent scavenge is really just a load thin range check. So the side, of course, the side effect of this load is the range check. Then we can conditionally call GC interface to finish the required GC work according to the range check results. So how are rebarriers generated? Well, think about this. I think the idea seems very simple, so that we can just simply replace the reference load from heap with their corresponding rebarriers. So it seems very intuitive to do it in the IOGen, but however, like as in new opcode, especially a generic opcode with arbitrary side effects, it is very hard for the optimizers to deduce any information or perform any transformations. And what is worse, the rebarriers behave differently for different purposes. For example, the rebarriers for the concurrent scavenge behave totally different from the ones used by FailWatch. So, well, therefore, optimizer doesn't cope well with rebarriers. And teaching optimizer about the rebarriers would be a very resource demanding, that the multiple transformations have to be touched, and we didn't have enough resources at that time, and we couldn't afford the risk at that time either. But like concurrent scavenge is meant to improve performance. We certainly cannot accept a solution that troubles the optimizer. Fortunately, the solution isn't complex. Well, similar to the compressed graph support, we don't have to generate we don't need the rebarriers, and we don't need the rebarriers at all before coding. So we can simply don't generate them until the coding. So once the optimizer finishes work, similar to the compressed graph, and during the codegen's lower tree phase, we will walk the trees and visit all the 8 load I nodes, and then use all the information that's indicated to guess if the load is a reference field load. The word I failed to guess was because once we reach coding, we don't have a 100% reliable information to tell whether a load I is indeed a load from a reference load from heap. So, but we can do the best guess and the most conservative guess. So then, if we think that a load I is potentially is a reference load from heap, then we replace the node with the right area. So so in this way, like the rebarriers are totally transparent to the optimizer, and therefore the optimizer can perform the same transformation as if rebarrier don't exist at all. Well, indeed, the rebarriers don't exist at all during the whole optimization sequence. So that then we can achieve, well, we can get the rebarriers functional work and avoid confusing the optimizers. So yeah, now I'm passing the presentation to Jimmy. So he will talk about how coding handles rebarriers.
Okay. Well, I'm going to be talking about the cogen section of concurrent scavenging. So I'll be talking about the code gen section of the concurrent scavenging. Okay, to get concurrent scavenging to work, we had to, I'm going to introduce a few of the functions and variables that we use. The first one here is called the function should generate read variables for field loads. This is a function that can be used when compiling a method that tells the JIT if concurrent scavenge is even active at the moment. So if concurrent scavenge is not active, this function will return false, and the JIT will know that it doesn't need to generate any of the associated root barriers or checks. And if concurrent scavenge isn't able, this function will return true. Concurrent scavenge on CodeGen also takes advantage of several fields inside the VM thread. The first one here is called read barrier range check space. Read barrier range check space indicates the lowest address of the range of objects that have not been moved, of the address space that contains objects that have not been moved yet. And read barrier range check top indicates the highest address. So if when we attempt to perform a load on an object and we get an address that's in between these two values, then we know that the code needs to call out to the read barrier to handle the object. These two fields also come in compressed ref version. If compressed ref is enabled, then read barrier range check space compressed and read barrier range check top compressed. Sorry about that. Read barrier range check space compressed will contain a compressed version of read barrier range check space, and read barrier range check top will contain a compressed version of read barrier range check top. That's a bit long to say, so I'll frequently just refer to them as base and top from now on. The compressed versions are convenient because they can be directly compared against compressed objects without requiring them to be decompressed. These VM thread fields are only updated just before or just during the stop-the-world phases, just before and just after concurrent scavenge is in progress. If concurrent scavenge is not in progress, then these four fields are given special values that they won't normally have. So you can see here that the range check base and both the base and the base compressed are just set to the maximum unsigned value, while the two top values are set to 0. These values are convenient because these fields can be checked by JIT code at runtime and can be used to check to see if concurrent scavenge is currently in progress. Okay, so another thing I need to introduce is the J9 read barrier VM helper. When JIT code performs a load and thinks it found an object that has not been moved yet, it wants to call out, it needs to call out to the J9 read barrier helper to address the potential issue. The read barrier helper is passed the VM thread and the address of the location we just tried to load from. And if the object has already been moved, the helper will just update the value in the load location with the new value of the object. If the object has not been moved yet, then the VM helper will help move the object before updating the load location. After the VM helper is done, it will jump back to the mainline code. And the mainline code needs to redo the load to get the new value that was just updated by the VM helper. All right, and here's an example of pseudocode that represents code that might be generated by the iReadBar or aReadBar evaluators. As I mentioned before, the iReadBar evaluator will be used in cases of compressed ref, and the aReadBar is used in case of non-compressed rest. You can see here that first that a load is performed to get the address of the object. The address of the object is then compared against base, read variable check base. If the address is greater than base, then it jumps to the outline read barrier. The outline read barrier then performs the second half of the check. It checks the address of the object against the top value. If the address is greater than the top value, then that means it is actually outside of the range. And outside of the range, it just jumps back in. However, if it gets to both these checks, so the object is both greater than or equal to base and it's not greater than top, then that means the object is still inside the range where object needs to be moved out. As a result, the code needs to call the read barriers to either to potentially move the object, but ultimately update the load location to, and then after that, the code performs load again to get the new value of the object before jumping back in and performing the rest of the code. If you look at these nodes here, the one beside base and top, this particular case represents the non-compressed case. But for the iRead evaluator to handle the compressed case, this would have to use base compressed here and top compressed there. Okay, other than loads, there are other special cases where a read barrier may be required. One such case is the concurrent swap recognized method. The concurrent swap, first off, this is the concurrent swap object has 4 parameters. This is the first object here, and this one here is an offset. The first object and the offset is used to calculate the load location, where the code will try to load from. The second object here is then, after we perform a load from load location, we get the loaded object. The loaded object is compared against the second object here, and if they are the same, then the third object here is atomically stored back to the load location. The second and third object, before we get to this point, would have already gone through a read barrier. But this is not the case for the first one. So this is a special case where we need to add additional read barriers to handle the load location from the object and the offset. And this is pseudocode to represent that special case. It's actually very similar to the case for handling the I read barrier and the A read barrier. The object plus offset is used to get the location to load from and then reload from that. Similarly to the previous case, we check against base and then go to the outline and then check against top. And if the object falls between base and top, we go to the read barrier again to update the location before jumping back. A slight deviation from the previous case is it is not necessary to redo the load right after redo the load. The reason for this is the concurrent swap will already reload the value. And once again, similarly, the compressed depth version will use the compressed depth version of base and top here. Okay. Another special case is for handling an array copy of objects. One way we could have done array copy of objects is to individually load each object, check them against the bytes in the top to see if they're inside the regions when objects need to be moved, and then potentially calling out the read barrier after that, and then after all that, maybe storing the value back to the new location of the array. But the problem with this approach is it can potentially require a large number of helper calls to the read barrier helper, which is expensive. Instead, we opt for a different approach. The approach we taken here is we check to see if concurrent scavenge is in progress at all. If concurrent scavenge is in progress, then we give up on trying to perform any part of the array copy in GC code, and instead just call out to reference array copy helper in the VM. And the reference array copy helper in the VM will take care of the entire array copy before coming back to the mainline code. Once again, I have pseudocode here that represents potential code that can be generated. If you recall back, read variable at top is given a special value of 0 when concurrent scavenge is not in progress. And we can use that to make a check inside GC code to see if it's 0. If it's not 0, then that means concurrent scavenge is in progress, and we can go to the outline helper. The outline helper will make a call to reference array copy, VM helper, which will perform the array copy, before jumping back to end and just going on with the rest of the code. But if the top is equal to 0, then we know that concurrent scavenge is not in progress and thus not moving any objects around. So it's safe to just use original GC code method to perform the array copy before going on to the rest of the code. Okay, and now I will be passing it back to Yan to talk about performance results and future work.
So Jimmy touched upon performance consideration in reference array copy. So that brings us to the performance tuning effort and discussion of future work. So thanks to the excellent implementation of hardware-based CS on Z, we know from the get-go what our goals will be. So we were shooting for a small throughput penalty, less than 10%, and a significant response time uplift between 40 to 50%. And the benchmark we use is called Factory 2015. It is a standard industry benchmark that measures both throughput in benchmark terms called max JOP and measures response time in benchmark terms critical JOP. And both throughput and response time are scored in units of operations per second, and both scores are the higher the better. There are many different areas that were scored during the performance tuning effort. I just want to talk about two that might be of interest. They are the heap size tuning and also the concurrent background thread, concurrent scavenge background thread concurrency level tuning. And of course, this performance tuning is always a work in progress. So we are using a 14-core Skylake machine SMT2, so 28 hardware threads for this exercise. So initially, we were setting our nursery heap size to 10 gigabytes, and the overall heap size to 18 gigabytes. So 10 gigabytes sounds pretty big, but under this workload, under peak injection rate, 10 gigabytes of nursery turned out to be a bottleneck. It caused the concurrent scavenge cycle to kick off far too frequently. So a concurrent scavenge cycle will kick off and then finish, and almost immediately another one will kick off and then finish. So they're happening very, very frequently. The implication of that is because we now spend most of the time the application running in concurrent scavenge mode, the application, as you remember, had to execute pay some kind of a tax in copying all those objects while it tries to load an up reference field. So under a 10 gigabyte nursery size, our throughput number, the gap between GenCon and scavenge was still pretty big, around 25%. And then for our response time, the concurrent scavenge only shows a very slight advantage over the regular GenCon. So next thing we did was we started to increase our heap size. So we went from 10 gigabyte nursery to a 16 gigabyte nursery, and at the same time, we increased the overall heap size to 27 gigabytes because we don't want to run out of space in tenure. That would cause global GC, which will be very problematic. The whole point of using a GenCon is not to have any global GC. only the nursery collection, as you recall. So under the 16 gigabyte heap, the concurrent scavenge kickoff was able to be less frequent and further in between. So in that case, the application thread has more breathing room, so they are able to run without paying any extra tax of concurrent scavenge. So that way, the throughput number, the throughput gap got smaller. We were still 20% behind, but look at the response time. That's where the concurrent scavenge response time starts to really show an advantage, noticeable advantage over regular GenCon. So in the next slide, I'm going to show you this graph rearranged such that on the left-hand side, you have the throughput and response time of GenCon. Right-hand side, throughput, response time by CS. So in this graph, basically you can see the score of critical GOPS as a percentage of max GOPS. Under GenCon, critical GOPS is only 45% of max GOPS. But look at CS. Under CS, the response time score is 87% of the throughput score, which is really high. What that 87% means for this benchmark is out of all the transactions that's completed during the peak load, a vast majority, 87% of them, is able to finish within a very short period of window. So that really speaks to the excellent quality of service characteristic of the scavenge policy. So that is heap size tuning. The next thing I'm going to talk about is the concurrent level, CS background concurrent level tuning. So as you recall, in my earlier slide, I talked about the concurrent scavenge timing. So during a period when concurrent scavenge is in progress from here to here, we have both the application thread and the background GC threads running at the same time to try to, copy all the live objects over to their appropriate destination. So what if we increase the background CS threads amount? What's going to happen? So because now we have more concurrent scavenge background threads tracing the object reference tree, we are able to finish the entire tree in a shorter period of time. So that will make the concurrent scavenge collection cycle shorter. So because the concurrent scavenge collection cycle is now shorter, what that means for the application threads is they spend less amount of time having to pay the extra tax of having to copy every object that they came across. So that will basically help with the response time and throughput. So that's a positive. Is there a negative? So now we are putting more threads on the same hardware. So what that means is there are now more threads containing for a fixed amount of CPU time. That will put more pressure on the operating system scheduler, and there will be more overhead for context switch. So all this could potentially lead to lower throughput and response time. So that is the trade-off. So we went ahead and did the tuning. So on this 28 hardware thread system, we tuned the concurrent background threads from 7 threads all the way to 26 threads, very close to the machine hardware. So we found out as we tune the concurrent background thread level, as we increase the concurrent background threads, they will increase, and then they will plateau at a certain threshold. Go past that threshold, both the throughput and response time will start to drop. And it turns out the best throughput and the best response time happens at around, if you set the concurrent background thread to 70% of the hardware thread. And as you can see, under peak number, with the gap between Concurrent Scavenge and GenCon is less than 10%, and that of the advantage of Concurrent Scavenge for throughput is around 45%. So this tuning basically brings out sort of the best in throughput and response time for Concurrent Scavenge. So I'm going to show you some tabulated data and graphical data for the pause time characteristics of regular GenCon and Concurrent Scavenge. So on the top row, you have Concurrent Scavenge, and this plot means the average amount of GC pause is only 6.3 milliseconds. And the second row, the average amount of pause time for Scavenge is 142 milliseconds. So the advantage is very obvious. If you plot those pauses on a graph, as you can see, the Concurrent Scavenge number, the pause time, hovers right around or below the 10 millisecond mark, and the regular Scavenge is way up there. So that really speaks to the high response time advantage of Concurrent Scavenge. So now I'm going to talk a little bit about future work. Both the GC team and the J teams are working very hard to trying to improve our Concurrent Scavenge technology, and I'm going to list a few. From the GC team, we are trying to further minimize the amount of initial and final pause, making the pauseless GC truly pause less and less. And for the final pause, we are going to take the remember set processing out of the final pause into the concurrent phase of the CS cycle. And for the initial pause, we are going to take the scanning of, we're going to take the scanning of the static field, static slot, out of the initial pause and into the concurrent phase of the CS cycle. So from the JIT side, we are working on runtime patching of the range barrier check code. So currently, the range barrier, the range is obtained by indirect load, as Jimmy was talking about, our indirect load of the VM thread. And using patching, we can basically materialize the boundary directly into the bound check instruction, do away with a indirect load. And again, from the GC team, we're trying to reduce the probability and the cost of a CS abort. CS abort is a situation where you find the object you want to copy, but you run out of space in both the survivor and the tenure space, meaning that you have no place to copy the object to. So in that situation, you will have to stop everything, stop every thread, including the application thread and GC thread, roll back everything you've done so far, and resort back to a costly global GC. Obviously, this situation is very costly, so we are trying to improve upon that. And also, the GC team is working to apply the concept of a concurrent scavenge into a global collection, making the global collection a concurrent affair as well. So with that, we conclude our talk.